Hello, everyone. Welcome back. So our first speaker in this afternoon will be Professor Claudio Castelnovo, and he will continue his lecture from yesterday. Let's welcome the speaker.
Thank you very much. I made a few changes to today's presentation in relation to some of the questions and comments that I got yesterday. So I thought I'd try my best to address them, and there was something that came up. It was really nice to discuss with many of you. And so I remind you the plan of today's lecture is picking up from where we left last time, barring a couple of additional slides at the beginning, looking at this standard model for spinized dynamics that we started to paint the picture of, and we'll discuss how it compares to experiment. That's more or less where I left, and I put up.
Like a high energy physicist.
What's that?
You sound like a high energy physicist.
Because of the nomenclature. We were looking for a name for it, and I just thought it would be okay. So I'll start then with the last slide we had, discussing how the standard model compares to actually experiments and showing it's actually good. But if we look under the hood, there's something missing, and we'll try to revisit what could possibly happen. I'll mention briefly what has been tried over the past 10, 15 years to solve this puzzle. And in particular, I'll discuss the direction that we went into of revisiting this microscopic timescale distribution. We'll find a surprise there, and we'll understand this and how it leads to a revisited model for the dynamics that will be able to explain, in fact, the experimental data, and I'll leave you to be the judge of how well that matches or doesn't match the data, and the reason for the change in behavior being underpinned by this emergent dynamical fractal that at this point in time it sounds very perhaps strange or confusing, and hopefully by the end of the lecture it become a clear topic, a clear understanding of. Okay, so this is the summary of what we had in our first lecture, and I'm not going to go over it, but just to remind, as a flash, like we have this spiral lattice, and then we have this exchange and the polar interactions, which I didn't specify, but in this talk I will actually illustrate and write down Hamiltonians for a bit more in detail, that lead to your low energy state as 2 into out. It's captured by a Coulomb phase, and then if we look at the energy states above it, still at relatively low energy, but away from this very lowest set of states, we find this peculiar instance of fractionalization where the spin flips breaks down into deconfined point-like particles that carry an emergent gauge charge as well as a piggybacking magnetic charge as coupled to the real U1 E&M field compared to the gauge one of the spin system of arrows, which is a way to describe the configurations. What I missed last time, that was pointed out I should have shown really, is that the prediction of this understanding of the low-lying states as a Coulomb phase led to this magnetostatic type field theory. It has this emergent U1 symmetry indeed, so it's a gauge theory, and it leads to the prediction of the spin-spin correlator, also known as static structure factor of the system, to have this peculiar form. And if in particular you think about the SZZ correlator between the Z components of the spins, well, this is QZ square over absolute value of Q square, so it's cosine theta squared type behavior. And so if you look at the Brillouin zone centers in reciprocal space and you go around it, well, cos square theta has a double periodicity as you go around, and so you will expect intensity patterns of this type. They're essentially saddle points. You go from maximum down and up again in this direction, so therefore the central point is a minimum, and in the other direction it's a maximum. And then you can, after quite a lot of effort actually, because it's not an easy measurement to do, this is what you get from neutron scattering if you want to probe indeed this structure factor correlator. And it was really one of the key signatures, one of the early ones that allowed scientists to say, like, they had found at least a spin-ice material that operates in this high temperature, well, sorry, dephased, I should say, not high temperature, dephased classical stat-mech limit. And indeed, you recognize these features happening in all of these points. Of course, to go from here to here, you need to put in lattice information in that formula, but that's just a matter of Fourier transforming the lattice program. Okay, this is one bit of information I didn't say yesterday. This is the confirmation, really, that experiments are behaving as the model that we put together, and that this form of the field theory, here we are not talking about rigorous nor exact, we're actually talking about a different type of approach, problems that are too tough to tackle otherwise, where you make informed guesses of effective theories, and you verify a posteriori whether they have any bearing to the reality of the model itself, and in this case of the material. It seems that we are on the right track of having the correct ingredients to describe this system. Okay, if you have any questions like yesterday, please interrupt me all the time, anytime, and just kind of to keep it going as a joint discussion. The other thing that we mentioned yesterday is the excitations. Again, picture from the earlier lecture. We can recast the language of a strongly correlated magnetic system into a Coulomb liquid, where magnetization changes can be interpreted and understood as monopole motion at low energy. And if we assume that there is some kind of dynamical, stochastic dynamics for these monopoles, with some characteristic time scale tau 0, one can produce what's known as a standard model for spin-ice dynamic. It's a Markovian process, and then you can try to solve it in different ways. We saw in the first lecture an analytical solution in the mean field limit. You can take a less coarse-grained approach, put it in a Monte Carlo solver, and of course, in this case, it's not numerical, no longer analytical, but you can keep track of the entire lattice. And you end up with an ability to describe the system and to make predictions that is significant. The important change being that you go from a strongly correlated spin system on a lattice to a sparse gas of particles, where understanding changes and becomes gives you access to a whole set of techniques and literature that a priori you wouldn't have correlated to a spin system, that of reaction diffusion processes, population dynamics, Coulomb liquids, etc. That actually gives you, oops, before I get there, it gives you actually a pretty decent comparison to experiments, in fact, and there are discrepancies. We'll come to that in a moment. But before we do that, one more parenthesis on something that Xiaogang pointed out yesterday. There is an interesting chicken and egg type question that one can ask in spin-ice systems. Imagine that you have some 2-in, 2-out state with these two monopoles in that corner, and then we fix the red one and we just move about the blue one, and this is one possibility of moving it across, right? And then what we know from the gauge theory, these are gauge charges, therefore there is an entropic attraction between them. What that means is that there are fewer configurations of this type than there are of that type, and therefore entropy favors the particles and antiparticles to be next to one another than apart. But statements like this about entropy relate to the number of configurations that are compatible with particles being at given positions. Now, if the particles are the only thing that moves and changes a configuration, your background is completely frozen. And so there is an interesting question: does entropy actually act to pull them together when they are the particles themselves are the only thing that actually changes the background configuration? So it turns out that if you can ask this question explicitly in Monte Carlo simulations, where you let this blue monopole walk around the lattice, you sample the probability of this monopole to be at a certain distance from its counterpart in red, and then you plot this distribution function as a function of the separation. And the entropic interaction means that there is an attraction 1/r potential that pulls them together in 3D, and therefore e to the -1/r is the probability of having them separated by a certain distance, e to the +1/r, And so if you take the log as a function of distance, inverse distance, you should find a straight line. And the prediction from the Coulomb attraction is that yellow line there, the simulations are the black data points. So you see that actually it does work even in the limiting case where there is only one monopole moving. The typical background configuration is sufficiently typical that it enacts the effects of the entropy, even though you're not actually doing an ensemble average of the configuration. And this is another instance of something that you're probably familiar with from other contexts as a notion of self-averaging. The fact that if you have a large enough system in a disordered state, a typical configuration is as good as an ensemble average over them.
Do you have a simple explanation why there are more configurations where they're close?
Yes, it relates to the magnetization again. So in order to move a monopole, you have to do the same operation of reversal, because if it's a positive monopole here, it has an arrow coming in, you reverse it, the monopole is here, then you have to take an arrow in, you reverse it, and monopole goes there. If you notice this red line, all the arrows are downward. Yeah, they go right, left, but they are downward. So the displacement between the two monopoles is a line of polarized spins. The more they displace, the larger the magnetization, and we already understand, generically speaking, that the larger the magnetization, the less favorable the configuration is from an entropic point of view. That's hand-wavingly. Of course, that doesn't tell you why it's 1 over R rather than other forms, but it gives you an idea of why that's favored. Okay, any other questions? Okay, so that's sort of like a cute just side remark. Oh yeah.
What is the y-axis?
It's the logarithms, it's log scale of the probability of finding these two monopoles at a given distance, and the horizontal axis is the inverse of that distance.
And where the single versus background plane?
It's single where?
The single configuration versus background.
Oh, this is generated by taking a given configuration. So this is entirely in a single configuration, and the only thing we are letting is that this blue monopole is free to move according to the rules that are dictated by the spins, but it moves around. So the configuration is fixed up to the motion of the monopole itself. Whereas entropic attraction is typically stated or thought about as to say the monopoles are fixed, and then you sum over all possible configurations compatible with that. Right? And it's a chicken and egg question of whether the two behave the same. Strictly speaking, the entropic attraction, you would have to sum over configurations, but what nature does is moves particles around. It doesn't update the system.
So there are no loop moves.
There are no loop moves at all, exactly. Of course, if we did loop moves, we knew this would happen, because that's exactly changing the configuration while preserving the position of the monopole. In that case, this law is expected from the field theory. But it's interesting that you don't need it, because the system is sufficiently self-averaging that the typical configuration already shows that behavior without the need to sum over configurations. Of course, this is configuration dependent. If we learned in the previous talk about exceptional states, Carr states, etc. If we had started from a fully polarized state and you put two monopoles, the monopole would actually repel linearly because that's such a peculiar state. It's fully magnetized. It tries to demagnetize as quickly as possible. So if you give it a chance to do it, it will. So it's not, but this is a typicality statement. Okay. Closing this side note that I thought would be anyway interesting to go over, let's go back to this standard model of spin-ice dynamics. People implemented it, in particular, Joubert and Holdsworth worked a lot on this and trying to look at response properties, magnetization response, for example, susceptibility, etc. And one of the typical comparisons that you would find that if you have to look at the literature of dynamics in spin-ice, up to very recently, would be the relaxation timescale of the system as a function of temperature, where you can measure it, for example, for those of you who are familiar with it, you can do AC susceptibility, you take the imaginary part of the AC susceptibility, and if it has a single well-defined peak, the position of that peak at that frequency is the inverse of the time scale on which the system responds. There are other ways of measuring relaxation time scale. You can measure magnetization response on stepping the field, but it's usually more difficult than doing AC susceptibility. Either way, however you get it, you have a time scale as a function of temperature. This is in real units because it's real material, that's seconds, and this is Kelvin. And the experimental data are the crosses. Well, there are data from 2004, there are lots of other sets, but those are the ones that I'm quoting. The leading behavior that we can even get analytically is just simply this characteristic time scale tau 0 times the inverse monopole density, which is they are activated excitations, therefore it's exponentially suppressed, and therefore tau is exponentially growing. That's the red line here. So we see that it's already a decent agreement. It's obviously mean field, it's missing a lot of details. Remember that monopoles can move only across majority spins, not the minority one, and of course at mean field level you don't see any of that. If you then instead put everything into Monte Carlo instead of doing mean field, you capture the lattice specifications, and then you get, depending on different types of models, you get these blue dots essentially here. And you could argue that it's a pretty good description. High temperature, this physics is very well understood. It's single ion physics that goes beyond this easy access easing kind of degree of freedom. And so we can safely disregard it. We know what it is. I mean, these are not real spin-a-half objects. They are very large J moments. They have a ground state doublet and a gap above it. And at these temperatures, you begin to see the excited state because they are thermally populated. Below this temperature, you're projected down on the doublet, so you have a good easing approximation. And the fact that it's flat here suggests that this doublet has some quantum mechanical matrix element to reverse its direction. That's what gives rise to tau 0. This is quantum mechanical because it's temperature independent. Had there been a thermal process flipping it, you would have a temperature dependence already here. Then this uprise here is no longer a single ion behavior. That's the collective behavior that we understand. Monopoles are facilitators of the spin dynamics. The fewer, the slower the system. Okay. So this is what was considered good. But if we actually look a little bit closer and a little bit more in detail, there are some cracks that appear. I mean, if we zoom in on a low temperature portion of this, oops, wrong direction. The experimental data now in magenta, and comparing the standard model, you get the gray line there. They look okay, but clearly not a good overlap. In particular, the experiments are growing faster than the simulations. And of course, if we know that that's an exponential, you can always say, okay, let's make delta larger. But this is the problem, and the beauty of these systems that the samples are very clean. There are lots of data, and the Hamiltonian for this system is very well understood, and it has excellent comparison with structure factor, all equilibrium properties, specific heat, etc. So if you go and change the energetics of the system, you have to then go back and check that you haven't messed up the comparison to all other experimental measures. So changing the Hamiltonian parameters is something that has to be done with care because it has to be consistent with a lot of other measurements. And there's very little leeway, and certainly not enough to increase delta to the growth here. Notice this is log scale, so you need a factor of 10 at around 0.7 Kelvin. Okay, more importantly, instead of looking at a single time scale, which is a bit reductive for a collective system, maybe there isn't really a single relaxation and response, you can do what's known as the power spectral density as a function of frequency. So this is take the magnetization of the system. You can measure the time trace of it, for example, using a squid. You measure the magnetization as a function of time. Take the Fourier transform, absolute value squared, that tells you the intensity of each frequency mode in the response of the system. And then you can do that in equilibrium, and you get what's known as the power spectral density. And these dots are, again, 3 different experimental temperatures from actual data. And if you run your standard model of spin ice dynamics, you run Monte Carlo, one thing that you get is that the typical form of the point spectral density is this Lorentzian, which has a high frequency tail that is omega to the -2. And that's extremely robust. You can do a lot to your Monte Carlo. It will not change this. You can put disorder, you can change the interactions, etc. It's really difficult to depart from this. And when you try to compare it, that's the gray line there for the same temperatures with the best possible Hamiltonian parameters that are known from thermodynamic measurements. And at high temperatures, you could argue that the disagreement is not too bad, but by the time we go to 0.65 Kelvin, like, it would be hard to say that you have captured the physics of the system. So there is something that is missing. Interestingly, the slope of the experimental data is departing from this omega to the -2 behavior. This is log-log scale towards, this is just a guide to the eye, not a fit, omega to the -1.5, right? So that's what people have been trying to understand. And the conundrum has been there since 2011, essentially. And there've been a lot of effort trying to think of whether if you're talking about real samples, you can have boundary effects, you can have disorder, substitution, you can have some colored noise origin in your stochastic dynamics. Many options have been investigated, and they can give rise to some form of agreement, but they tend to bring in a lot of parameters that are users fitting to the data, and none of them actually gives a pretty thorough match to the experimental curves over the whole range of temperature and frequency and intensity. Notice that we have a lot of scaling to fit. Look at the axis here. We have about 5 orders of magnitudes in frequencies, about 6 in intensity. So that is a good place to be as a theorist because, well, or maybe not, because either your theory matches it or you're in trouble because you have a lot of data to go by. Okay. Any questions at this point? Okay, so that sets the stage for what we did. To be honest, actually, we've spent a lot of years trying to do this and failing, so it's not like just this. But eventually, we thought about going back to the basics and looking at the spin dynamics. And as I said, this regime being flat suggests that there is some matrix element or quantum mechanics involved in the way that these spins reverse, and that's what would give rise to the elementary, microscopic timescale tau 0. Yeah.
On the previous slide, is there a value of beta the experiments correspond to?
So later I'll give you a theoretical proposal. Here I just drew a line, omega to the -1.5, and you can tell me whether you think that's fair or not. It's a guide to the eye, it's not a fit. And I'll explain later why I picked 1.5, obviously. But okay. So we're looking at matrix elements, and what's the source of matrix element in easing spin dynamics could be potentially interactions. So that's where we went back and thought about thinking about the picture of this is that you have large crystal electric field, that's what they are known as, the environment of a sort of orbital overlap around your magnetic ion that forces it to be pointing along the so-called local 111, or what I call z-axis, in or out of a tetrahedron. But then you have dipolar and exchange interactions, exchange to be defined, however many details we want to put in that term. The dipolar is more standardly written this way, and these are not bound to operate along the easy axis. So if you think about the sum of all the spins acting on this one, they'll give you some effective, if we think about classical spin, effective vector direction interacting with it, or in general, they're not going to act along the axis. And if we can then decompose that into a longitudinal component, which will be a preferential local spin direction, and a transverse one that gives dynamics. That would be the matrix element that you would have in a quantum Hamiltonian that gives rise to time evolution of your system, of your spins. So this is a complex problem, but it's actually what I will be coming to is illustrated very nicely if we just simplify it to an S.S simple Heisenberg type interaction. So that's what I'm going to do first, and then I'll come back to dipolar as well as more proper exchange terms for these complex materials. Let's reduce the system to a nearest neighbor S.S interaction with some minus coupling minus J. J positive, remember that the vector S are frustrated if you put them ferromagnetically coupled, which is antiferromagnetic in the sigma variables, interestingly and confusingly enough. Then we can trivially rewrite this sum over nearest neighbor as the sum over all sites I, Si dot the exchange field, which is the sum over all its neighbors, and I labeled the central site 0 and the 6 neighbors 1, 2, 3, 4, 5, 6. So that's what I have here. The parentheses are suggestive of what I'm going to say in a second. And there is a J over 2 for double counting if you want. So that's something that should be trivial or you've probably seen before. Now, in this geometry, it's interesting to focus on this exchange field because if you look at the various spins, they all have different easy axes, but they are pairwise the same. S1 has the same axis as S4. Now, in this picture, particularly the same direction, but that am I referring just to the axis now? 2 and 5 have the same axis. 3 and 6 have the same axis. That's why I wrote them that way. The sum over all the 6 gives me, in this specific configuration, the arrow shown here in green. I have picked a very specific configuration because it's the one I'm interested in. It's a configuration that has a monopole here, 3 in, 1 out, 2 in, 2 out here, and this is a majority spin. That means that the monopole can move free of charge, free of cost. And the fact that it can move free of cost tells me that the transverse field has to be exactly perpendicular, because if it was longitudinal, you would have a bias, right? So it's no longer free to move. So the sum of this gives you a transverse direction. That's good. We are at least consistent. And this transverse component is what gives the matrix element for this spin to reverse itself. However, we can then look at all possible symmetry inequivalent configuration of the 6 surrounding spins that are compatible with this tenet of having a monopole that can hop from the bottom to the top tetrahedron. And there are 3 inequivalent classes shown here. That's the one I had before. This is another option, and that's the green arrow. And this is the third option, and there's no arrow. There's no arrow for a very simple symmetry reason. It's with respect to its 6 neighbors, this configuration is perfectly centrosymmetric. So S2 is oppositely pointing to S5, S1 is oppositely pointing to S4, S3 is oppositely pointing to S6. If you have that, these 2 cancel, these 2 cancel, these 2 cancel, and the transverse field is exactly 0. So you have a very peculiar situation where, for a typical monopole here, in a context where it can move up, depending on its neighbors, depending on the local spin correlations, there may be a matrix element for this hop to happen, but there actually might be none. And so if we take this model face value, S.S, you would have to say that if you're thinking about endowing the system with dynamics, these 2 local configurations have a very different dynamics from this one. They're actually, the magnitude of the green arrows is the same. So they have the same magnitude of transverse component and the direction doesn't matter. This one has 0, so it doesn't. It's one of the peculiar situations where you have a quantum spin pointing in one direction. You have 0 matrix elements, therefore it doesn't move. Even if it can freely rotate, it just doesn't. You can argue, okay, this is a peculiarity of an S.S model. We know these systems are really not S.S, so is this something, is it a flaw of this type of simplification? Well, what I said a moment ago should give you a hint that it isn't, because it's based on the symmetries of this. But let's first look at it one at a time. I mean, if we look at dipolar interactions, they can violate that because they are longer range. So the centrosymmetric structure that you have here, once you start adding all of the neighbors, it's very unlikely to find a configuration that would be fully inversion symmetric. And therefore, you'll get corrections to this. But if you have a monopole, ignore this panel. That's for spins away from monopoles that are not of interest right now. Next to a monopole, you have this is a probability histogram essentially of the transverse component of the field and the longitudinal one. And you see that what we had earlier as delta functions of two values, 0 and some finite number of the transverse field, now they broaden out, they get spread out. In particular, the 0, 1 gets moved away because the longer range interactions will give rise to some matrix element, but there is a clear separation of scales between the 1/3 of the configurations that are at nearest neighbor level inversion symmetric and the ones that are not inversion symmetric, where you have a sizable transverse field, a sizable set of matrix elements. If we want to go into exchange Hamiltonian, we can then pick our favorite exchange Hamiltonian. We can stay in the ground state doublet, or actually we can go beyond, and if people are keen on seeing what the Hamiltonian looks like for interactions between this type of spins, you have, well, this is a schematics for praseodymium, which is even simpler than dysprosium. But anyway, you have F moments here and here, and the super exchange is a 4th order process with the intervening oxygen. And on top of that, so this is the process that you have F2, P6, F2, and then the super exchange all the way back to the configuration. And on top of that, the 2F moments have local reference frames that are rotated. So in addition to all the rest, the other parameter, you have rotation matrices to match the 2 reference frames. Ono and Tanaka did this calculation for praseodymium, and there was a graduate student back in 2018-19 that spent several months to extend it to dysprosium. You end up with ugly Hamiltonians in the fermionic language, but the calculation can be done, and the answer is the same. It's really this 2-to-1 ratio of this distribution of transverse matrix elements in 2-to-1 ratio, where one of them is vanishing at nearest neighbor distance, is a property of the symmetry of the configuration. And so it withstands even the sort of most realistic form of exchange interaction that we can think of in these very complicated systems. So in summary, we have this bimodal distribution and two inequivalent types, one with transverse field 0, the other one with transverse field difference from 0, or I should call them really matrix elements, because with that exchange that I've just shown is not just a field, but it's a matrix element. In average, 1 in 3 is, let me call it slow, and that's fast. They are determined by the local correlators, and at nearest neighbor level, slow actually is no matrix element whatsoever. Dipolar gives you a correction to that, so I will call it tau slow for simplicity, but for what I'm going to discuss later, I'll take the limiting situation where p is 0, and therefore the time scale for flipping this spin is honestly infinity. So we don't have any flipping parameter, it just doesn't happen. So if you wanted to criticize or think about this type of analysis and argument, there is one important caveat to this that you should come at me with. If we look at what we have been discussing, we have assuming that the spins 1, 2, 3, 4, 5, 6 are in a given state, and we're looking at the dynamics of the central one. Of course, in a many-body system, dynamics is cooperative. By the time this spin starts moving, other spins can move as well. So under what assumptions am I allowed to essentially project the 6 neighboring spins to a given state and focus on the dynamic of the central one? Well, this is an interesting question. So there is an approximation that is there. Clearly, the faster the dynamics of the system is, the more spins will be moving simultaneously with respect to one another. In the classical limit of this very large dysprosium and holmium moments, it's this picture, we argue, should be correct or sufficiently instructive to propose this modification of dynamics, which is an introduction of slow or fast spin flip timescales controlled at a local level by the spin correlations. So there is no disorder in the system. There is no preceding what spin will flip fast or slow. at every moment that a monopole can make a hop, it should check its your Monte Carlo process should check its 6 neighbors and then determine whether that hop happens or not. Not if it's tau of this type, tau slow, and it has happened on tau fast, if it's possible. Yeah.
Is there any consistency requirement? So if one direction is slow to others?
No. So a good question. So it seems that this, on average, 1 in 3 is slow, but it's really on average. So monopoles can move only on the majority spins. So there are 3 majority, 1 minority. So 1 minority is deterministically blocked everywhere they are. So they only have 3 options, but those 3 options can be all simultaneously slow, 1 slow, 2 slow, all simultaneously slow, 1 fast, 2 fast, or 3 fast. So all options are possible. It's just a statistical average. 1 in 3 is missing a matrix element to flip. Yep.
So maybe I already said this, but it seems like the flipping is because of quantum operator that does not commute with the z cases.
Correct.
Then why are we treating these flips as incoherent processes?
Because in these systems, the moments are very large, and all comparisons to experiment and all experimental evidence we have to date suggests that treating them as incoherent successive flips is a good description. And so you can imagine this to be the limit where your spins do quantum precession, but this precession loses phase coherence before another spin starts also precessing in a significant way. Yeah? And therefore, the description becomes a series of independent stochastic spin orientation changes rather than coherent multi-spin quantum dynamics.
It's still a 2-level, like effectively it's still a 2-level system.
Yes.
So in what sense is it a large volume?
So it's in the sense that there is a crystal electric field, which I haven't written down, but it's the oxygens around this moment split the degeneracy between the levels of a very large J into a well-defined doublet and a big gap of several hundred Kelvin. So all the physics I'm talking about is sub-Kelvinish, maybe like sub-4 if you want to be generous, but not more than that. And so energy scales of 200 Kelvin or higher are essentially a big projector that says that physics is out of the window at the moment. So that's what happens. You have many, many MJ levels for J large, and you pick the lowest 2. Dysprosium has J equal 15 halves. Yeah. And to a good approximation, the ground state doublet we're talking about is actually minus 15 half and plus 15 half, approximately. So that's, yeah. Okay, so this gives us a very simple proposal on how to change your model. Doing analytics is hard because we need to keep track of local correlations, but doing Monte Carlo is relatively easy. We just have to implement this sort of clever Monte Carlo update that when it tries to flip a spin, checks the neighbors, and if the neighbors are of this type, rejects the updates on grounds of missing matrix element. And it's possible to do that respecting detail balance, so everything is fine. Notice that we can do that without changing the energetics of the system, without changing the Hamiltonian energy, etc. So therefore, the thermodynamic properties stay exactly the same. And we have introduced no new fitting parameter. Because earlier we had tau 0 that was our fitting parameter. Now we have tau fast instead of tau 0, but that's it. Tau slow is infinity, and that's not fittable. Then we can run the simulations and go back to the experimental data we had before. And the BSM is in black, the standard model is in gray, that's the one I showed earlier. And then, okay, you can tell me whether you like this agreement or not, but it has improved. And I stress again that, yes, there are departures here that may be significant and it'd be interesting to understand them better, but we are talking about 5 orders of magnitude here and 6 here. And you know, it doesn't happen often that we find such level of good agreement between experiments and well, theoretical simulations in this case. I stress again, same number of fitting parameters, both in the SM and the BSM, and the thermodynamics unchanged. So in a sense, it's just achieving an agreement by a small change in how the dynamics operates at the microscopic level. It's really remarkable that you get that much of a difference from such simple modification. And so the most interesting part is perhaps to go and see why this is happening. And that's essentially what we are gonna focus on next. But I'll give you a bit of a spoiler of what we think is happening, and I'll present evidence for it. Remember that the monopoles can only move on a three-dimensional lattice via the majority spins. So that means that for every monopole, there is already one blocked direction. Again, this is not disorder, it's dictated by how the spins are arranged. This is a completely clean system from a point of view of disorder or any other chemical substitution. And therefore, the monopoles are already moving on a little bit of a funny lattice, because rather than moving on a nice, simple diamond lattice, you effectively have removed one bond every vertex. So every vertex has 4 of them. One bond in 4 has been removed because it's not traversable by the monopole. So that's already something that changes the network over which the monopoles are moving. But it's a very, I would refer it to as hyper-uniform change, because it's exactly 1 per vertex. So you're not removing 1/4 of the bonds at random, you're removing 1/4 of a bond in a very systematic way, although it's still disordered. Now, what we have done by changing these dynamics and introducing slow, essentially static spins, depending again on local correlations, is that we have, out of the remaining 3 available directions per tetrahedron, we have removed on average 1. Now, if you take a lattice that is 4-fold coordinated, you remove exactly 1 bond and you remove on average another one, you realize that what the monopoles are moving on something that is becoming to be very sparse. In fact, if you did it statistically, you have removed 50% of the bonds and you would have completely disconnected the lattice. So the system should not even be ergodic anymore, because the monopoles can't traverse the entire system. The truth is that that doesn't happen precisely because the way in which you're removing bonds, and in particular the block direction, is hyper-uniform. So percolation requires random disorder. If there is correlation between the disorder, percolation may not happen. In fact, the percolation limit on the diamond lattice is 0.39. We are at 50% removal, but we are not there yet, and I'll show it in fact. But however, we have gotten just close enough from above to the percolation limit to begin to see the fractality of the network over which a monopole would move if the system were exactly at percolation criticality. And that's what is leading to this anomalous behavior and these exceedingly slow relaxation timescales. They are exponentially slower than what energy would dictate, purely on combinatorial, essentially, grounds of the sparse network over which the monopoles are moving. So nice words, but let's see how we actually demonstrate this interesting picture. The first is just a glance, non-scientifically if you want, but we can ask, give a monopole. Yep.
When you remove these bonds, you do that in a quenched way or in an annealed way?
It's inherently annealed, because we never remove them. It's a property of the spin correlations. So we look at the correlations, and as the very same spin may be flippable or not, depending on the neighbors. So if you have a monopole here that cannot go in one direction, if another monopole traverses the nearby tetrahedron, this direction might open up, and so on. So it's very much annealed inherently in that sense. Any other questions? Okay, so we can start with a monopole here, a given configuration, so it's sort of a snapshot of the system, and we can ask in 3 steps, how many sites can the monopole visit? And those are highlighted in blue. All other sites that it cannot visit are not shown. The different shades of blue have no significance. It's just a 3D rendering that does that. So n equals 3, that's the standard model. That's the beyond the standard model. N equals 6, you begin to see something. N equal 9, they become impressively different. N equal 12. This is block directions are not accessible, but clearly they remain dense in the original lattice, and this structure is a lot sparser. For n equal 12, the BSM can access about 1,000th of the sites that BSM can access. Yep.
This might be a very random question. Is this like a cellular automata process?
Like, yeah, you could map it onto it. It's like the question of, can I move in this direction based on the correlations, is exactly what a cellular automata would do. One of the direction is blocked. That cannot. It's a question that you can answer energetically. That would be a standard Hamiltonian process. And then there is the other one where is asking about transverse component, and that you can recast it indeed is in a sort of an intelligent local walker that says, okay, I'm going to work on this only if those 3 spins and those 3 spins behave in a certain way. Yep.
Why do you call this beyond standard model?
It's just a nomenclature, because the standard model is what we had before, where we didn't account for the transverse fields. And so if we account for the transverse field, we're going beyond that picture. So we called it beyond. It's just a name. Okay. Let's put that into quantitative measures. So this is the number of accessible sites as a function of number of steps from the starting point. And if we look at the standard model, you get this orange behavior. There is some lattice scaling effect, but then it falls into a dotted line, which is n cubed. That's what you expect. If you have a random walk in a 3D lattice, it visits densely the lattice as a function of steps, and the scaling of the number of sites it can visit is n cubed. This is the sites it can visit, not that it visits after n walks, all the possible accessible ones. If you look at the, let's take now an honest percolation problem. Take the diamond lattice and you remove bonds. Now you remove them as fixed bonds with the percolation criticality threshold, which is 0.39. And then you put a random walker on it and you let it go. On the critical cluster, you get these light blue crosses. And again, they have some lattice scale effect, and then they fall onto this dashed line, which is n to the power 1.85, and this is one of the fractal dimensions that you can indeed define for a structure. And then if we look at the beyond the standard model is the blue dots, and you see lattice scaling effect, a scaling of not even a decade, about a decade, on the fractal behavior before it realizes that actually it's sitting, in fact, above percolation threshold, and it goes and realizes it's actually dense. Yeah? So we just about touch on the criticality of the percolation cluster, but you realize you're not, and therefore you're dense on longer scales. But it's remarkable that this relatively small effect has such a big consequence on the dynamical properties of the system. And this is highly unexpected, and partly one of the reasons why this beyond the standard model picture wasn't investigated until much in very recent year, even though the model itself was known as a possibility since 2018. No one believed that this would make that much of a difference. Perhaps a better way of saying it is that in this regime, actually, the beyond the standard model monopole can visit only 130 sites, whereas the standard model around here is about 2,000. So really, it's actually making a big difference at relatively short distances. Okay, we can quantify this in other ways. So this is a number of accessible sites from a typical configuration. We can ask more random walk type questions. Put a monopole in a typical configuration, say at low temperature where there aren't many others around, and let it go and measure the displacement from the original position. If it's diffusive, then it's linear in time. The square displacement is linear in time. And this is what we see. That's the blue that line is the data, and then we have the asymptotics linear in t dashed line, and dotted is square root of t. So we see that we have initial subdiffusive behavior before the monopole realizes it's actually walking onto a dense lattice is really not at percolation exactly, and therefore it takes off with the standard diffusive behavior. How do we understand the anomalous short time regime? Well, it turns out that actually the problem of a random walker on a percolation cluster is something that was addressed, studied, and solved some time ago by exact enumeration of paths, and the exponent is exactly 0.5. If that's the most sensible explanation, a very loose hand-waving one that you could think about, otherwise, if you prefer, is that we have removed about half of the bonds. So the motion of the monopole is highly linear at short distances before it finds dead ends at branching points. And if you have a random walk on a random walk in 3D, you get double square root. So you would get that kind of behavior. If that didn't click, ask me in the break, and I can tell you how that argument goes. But it's actually very approximate. And this is the argument that we really want to go back to. From the random walk, we'd actually, there is a way to analytically to compute the power spectral density from the properties of the random walk of the particles that cause the magnetic noise. And so you can recast that same figure into a measurement of power spectral density. And again, we see the picture is consistent. The standard model is this orange line, which is omega to the -2. And then the percolation cluster would give you a light blue line here, omega to the -1.5. And then beyond the standard model has an initial, an initial high frequency behavior along the -1.5 scaling, and then it bends up towards -2 at low frequencies long times. So everything fits, and the relationship mathematically between the random walk and the power spectral density is such that the exponent 0.5 turns actually into 1.5, and the exponent 1 turns into exponent 2 that you see here. So everything's consistent, and it seems to withstand, and perhaps the picture seems correct, and then what's most surprising about it perhaps is the fact that this relatively transient time and length scale behavior has such a profound impact on the measured properties of the system and on the relaxation time scale as well. Okay, so are there any questions up to this point? And I have one quick slide left-ish. Okay. People mentioned what about quantum spin ice. Is a question that I've deferred a few times, and I thought I'd add the slide to come back to that. I showed you the fermion-fermion interaction Hamiltonian that is ugly. We had it a few slides ago. If you project that onto the ground state doublet, it takes a slightly better form, and I copied it here. This is the general effective Hamiltonian between, so you have this sigma z interaction with an antiferromagnetic coupling. That's the one we are familiar with. And then we see that there is a plus minus minus plus, so transverse term typically. And then there are a few terms that you wouldn't have expected for spin a half, and they're related to the peculiar structure of these materials. You have actually a plus plus and minus minus term with some important phase factors due to lattice symmetry locally. And for Kramer's doublet, which dysprosium is, it's a spin 15/2. You actually are able to write this term as well, which is allowed by symmetry. And written like this, it might not show it immediately, but it's essentially a sigma z, sigma plus type interaction. So if you wanted to try and tackle this problem from a quantum mechanical perspective, for dysprosium titanate, these are the two things you would put together. From a point of view of the physics we have been discussing and chatting about over the last couple of hours, yesterday and today, we have the many states that are low-lying to into-out states, and these terms in the Hamiltonian allow now matrix elements between them, so you generate a superposition of them. And what's interesting is that you manage to upgrade essentially your magnetostatics to actually compact quantum electrodynamic field theoretic description, and that's the basic understanding we have to date of quantum spin ice. How do you create superposition of two into-out states? You know that flipping a single spin doesn't work because that creates monopoles. The best you can do is create a monopole-antimonopole pair and annihilate it in a non-trivial manner, meaning around a loop. And the smallest of such loop is a hexagon on this lattice. You have typical sort of ring exchange processes that you may have heard of or are familiar with in other contexts. These terms will also introduce, if you have excitation looking inside the state, to a tight binding hopping terms to monopoles. And in fact, in the emergent QED, you also have dual charges. If we refer to monopoles as spin-ons, these would be your bosons if you want. As far as I'm aware, there's no anionic phase between them other than the standard QED picture, where, of course, if you have magnetic fields, they give a phase to a charge going around them, and vice versa for electric fields and magnetic charges in this picture. So what we have been discussing today, obviously dysprosium titanate is a real material, therefore it ought to be described by a quantum mechanical Hamiltonian. I have given 2 hours of lectures on classical stat mech. Where does that come from? The idea is that this J and N coupling is the largest energy scale, delta and Q are small and kappa are small, and therefore you have weak ring exchange processes, relatively weak tight binding of the excitations, but a strong energy that enforces primarily two into out, plus a small fraction of excitations with energy cost that I call delta. And if you imagine having coupling to an environment that dephases the system, the dephasing is able to spoil phase coherence from the ring exchange, therefore no longer a superposition of states, but you have individual states, and spoils the tight binding of the monopoles that therefore move in a quantum diffusive, or if you want, stochastic manner. So that's the picture that we have been having. If we want to reinstate a full quantum mechanical description, this is what we have to solve. It's tough. If we want to try and do something in between, there are a couple of considerations that I want to add, and I'll close roughly with those. The first thing is that if we put in ring exchange in a way that is coherent, so it can operate but doesn't create a superposition, we would introduce some kind of stochastic loop dynamics between the systems. And that has a very important effect in this model, because the disorder that was causing the fractal was really dictated by local spin correlations. So if you fluidify them by doing loop updates, you smear out the fractal into a generic probability of going, reduced probability of moving in any direction, but you make it now isotropic and uniform, and you kill the fractality and you kill all of the physics that we see. And in fact, if you run Monte Carlo simulations pretty straightforwardly, you can add loop moves and you add the fraction of loop moves per Monte Carlo update. For 0 is the behavior of the BSM that we are accustomed to, and then you do 1 attempted loop move per Monte Carlo update, 8, 64, etc., and then you compare. You see that the curves drift towards the standard model eventually. When you do enough loop moves, you just lose all of the physics that we are discussing. So if we went towards the quantum limit from this highly dephased regime, by adding loop updates, you would lose this physics, and something maybe to look into experimentally. The last thing is that if we were to then attempt to look at this QED picture where we have tight binding monopoles, then we would have to come back to this picture that we are thinking about. What happens if all of the physics we discussed is hidden in this Hamiltonian, but if we go to an effective picture of QED, emergent monopoles, and some tight binding, then we have to come back to the fact that the tight binding amplitudes are dependent on local spin correlations. And so you have a very strange cooperative type quantum dynamics that I have no idea how to address or solve, but it could be an interesting question at the quantum mechanical level. I can't say anything more than that, about that. Okay, so that I had these were the sales pitch of why all of this is interesting. The other two are pointless, but dynamics in spin liquids, generally speaking, this may be a good endpoint, is both of fundamental interest to understand how fractionalized excitations behave out of equilibrium and how they change the response properties of the system. But also, they are a very powerful tool to try and detect and diagnose these mischievous and difficult, sorry, no, mysterious, not mischievous, well, anyway, phases of matter. They're really hard to find, difficult to measure entanglement, difficult to measure in topological order. Excitations are more amenable to experimental approaches. So detection and diagnostics is interesting, but also if we think about quantum computing, some point there was a hype about topological quantum computing, etc. It's all hinging on the ability to manipulate, control, and move these excitations. And so then understanding the dynamics is fundamental from that point of view. And there's interesting connections to Glass's system and something else that you can ask if you want in the break. And I leave up the conclusion because they don't say anything that I haven't already stressed. I think in the interest of time, I'll stop here and I'll take any further questions. Sorry for
The quantum model doesn't look easy.
No, there is a reason why I stuck with classical.
Is there a quantum diagram picture of that?
There is, so you can write a Roxer-Kivelson type quantum spin-ice. So this is the same way that you can build a quantum dimer model a la Roxer-Kivelson. You can do the same for spin-ice, but it describes only the sector without monopoles. Same as in dimer models, by the time you add excitations, the quantum Hamiltonians become tricky, and I don't know how to tackle them. Yeah, that's fair enough. Same with large S. It's a good approach, but then it's not possible to put in spinons, and the visors are now solitons that move by instanton events, so we lose the dynamics of all of the excitations, essentially. Yeah.
Is there any other questions?
If not, like before we close, just a second, I asked permission earlier, I wanted to bring up, I thought this would be the right audience to say that. I want to bring up an advert for junior research fellowship positions in Cambridge at Trinity College. These are independent postdoc positions for 4 years. They can be delayed for actually up to 2 years, any point in time. So effectively, it can extend to a 6-year postdoc if you want to go somewhere else for 2 years. They give you research, accommodation, salary, and meals, and they are highly competitive. But if you're on the market, they have a very early application deadline. So I thought I'd flag them up, and there is a link here for that. Sorry for taking a further second.
All right, and then let's thank the speaker again.
Is it possible that
Yeah.